Okay, sir, we're going to start. Okay.
Okay.
So, good evening to all present here. I welcome our chief guest of the day for this lecture titled Challenges of Future Space Missions. Organized by Niti Aayog, ATL Incubation Lab, KV Air Force High Ground Center, in association with TEMS. Joining with us, we also welcome Honorable Principal and Vice Principal of Navy Air Force and founder and President of Society of Aero. So now I would like to introduce our chief guest of the day, Mr. George Salazar, has over 30 years of experience in telemetry, communications, speed control, command and data handling, audio display and control, intelligent lighting, project management, and system engineering. He has also involved in the design of advanced telemetry, voice recognition, and intelligent systems of which he has received various patents. He served as a subsystems manager for the Space Shuttle Modular Auxiliary Data Systems, a system designed to acquire Space Shuttle engineering data. He also was involved with the development of station internal audio systems as well as development of the command and the data handling flight computers and command the telemetry computers for spacecraft version of X-38 spacecraft crew-ridden vehicle. He also was a system engineer for the hardware development for the Space Shuttle cockpit avionics upgrade to provide more insight into the health and status of the space shuttle. He leads several advanced avionics technologies concept investigation for the next generation space program. I welcome you now and Wings of Arrow heartily welcome to all the supporters and participants. And I request George, sir, please take over the session. Please, sir.
Thank you for the kind remarks. And let me just get this into the presentation mode. All right. So thank you for having me and for inviting me. I enjoy speaking to students, and so hopefully this morning or your afternoon is going to be a little bit educational. If you walk away with one thing that I shared with you that is new and of interest, I think I've accomplished my job. So let me just talk a little bit about my presentation today. And you see the topics that I'll be talking about, but you see in the backdrop Star Trek, the Star Trek that came out on television years ago. I grew up watching some of that, and it's just amazing how far we've come since that time. I mean, that was all sci-fi and fantasy, but we're starting to become a reality. And one of the interesting things that I'd like to point out about that backdrop is the diversity of the crew, right? And so that's what it's going to take, to do our future space missions. It's going to take diversity. It's going to take people from all over the world. I mean, right now we got on space station something like 16 nations that are supporting space station, and so it's very representative of that picture of we're going to need, to go to the moon, Mars, and beyond. And of course, we don't have a Starship Enterprise and that kind of technology, but we're getting there. What I want to talk about today, as far as the topic's concerned, is I'm first going to talk about where we were as far as some of our past human spaceflight programs and where we are now with space station. And where we're going, is one of the biggies is the Artemis program, and I'll say a few more words about that later in my presentation. And what are the challenges and how to meet them? And so that part is, I think, is going to be of interest, and it's going to be one of the major factors that's going to determine where one day we boldly go where no man has gone before. If we can overcome some of the human reasons as well as the technology associated with that. So let me go to the next slide. And I'm just going to give a brief history of human spaceflight. Um, I don't know if you know or not, but the Mercury program was the first human spaceflight program back in the 60s. We had 7 Mercury astronauts. They were all military people. And the reason for that, because it was high risk. Not to say it's not high risk still, but back then we were still learning how to fly in space, and especially with humans. And the interesting thing about the Mercury program, we wanted to understand if humans could operate, live, and work in space. There was concerns about just eating food, whether the food would stay down. We didn't know that was going to happen. So the Mercury program provided that opportunity to learn about whether humans could live and work in space. And the Mercury capsule was just one person. No computer on that Mercury space capsule. The computer were on the ground, and they would do trajectories and orbits, that kind of stuff, and send those commands up to the Mercury space capsule. But then we go to the next space program, which was a very pivotal point in the human spaceflight, is the Gemini program, which we had to understand how to dock and rendezvous in space, and that was going to be critical going to the moon. So it became a 2-person vehicle. In fact, the complexity increased quite a bit because of the nature of rendezvous and docking. We're afraid that they would not have enough side to send commands to the computer during the time of loss of signal, LOS. And so they had the first onboard computer for Gemini to help them dock with a spacecraft. And so the Gemini program was very successful. It was a little bit more complicated than the Mercury program, but we learned a lot about docking and rendezvousing in space with 2 spacecrafts. And so we go to the Apollo space program. That's the one that landed the moon on July 20th, 1969. In fact, I think we're coming up to the 51st anniversary of that moon landing. It was a very complicated endeavor, but we did it. We had a total of 12 astronauts walk on or rather on the surface of the moon. The time spent there was not a whole lot. I'm trying to recall something like 11 days total, if you include all the time of all the astronauts. So it's a whole lot of time that we spent on the moon's surface, and that's one of the reasons we're going to go back, because we need to learn how to live on we just didn't spend enough time on the Apollo space program. Program after Apollo, and that's the one I started with, was the space shuttle. Space shuttle was an interesting vehicle because it looks like a rocket, orbited like a satellite, and returned to Earth like a jet air. Very complicated. I can give you an idea, somewhat of a complexity from the set of switches. So Mercury has around 55 switches total for the and displays for the astronaut. Space shuttle had over 2,500. It was just an incredible complex machine for that kind of. But it did a lot. It did a lot. It became a pickup truck, if you will, for the assembly of the space station. So. But again, if you look at Mercury, going from Mercury, Gemini, Apollo, and Space Shuttle, complexity increased quite a bit. So let's talk about the current human spaceflight programs. And this is current thinking right now is a phased approach to Mars. And so what you're seeing on the left-hand side is Earth. And this is basically what we call Earth-dependent operations. And in the middle is the moon. It's basically what we're calling the proving ground. Proving ground means that we are going to how to learn and live on another terrestrial body, the moon. And one of the nice things about the moon is it's not too far away from the Earth. And we go to Earth independent, which is Mars. And the reason Earth independent is it's going to be so far away that astronauts really have to rely on themselves and the ingenuity and creativity to solve problems, because mission control is not going to be immediately available to help them solve problems. And I'll say a little bit more about that later in my presentation. So let's just talk a little bit about the space station right now that's orbiting the Earth. It's a very large space, if you will, the largest ever built, about the length of a football field, 300 feet or approximately 300 feet. There's a lot of things to learn on space station that help us go to the moon and Mars. And one of the interesting things is that the microgravity environment, sometimes people call it zero gravity. Actually, there's no such thing as gravity. It's a microgravity environment, but there's some benefits to that. Is to understand how to make better materials and better medicines, if you will, that microgravity environment. In the one gravity environment that we live in now here on Earth, you and I are exposed to, is that there's some hidden things about density of atoms that don't show up easily in a 1G environment, but in a microgravity environment, they do. So, in the microgravity environment, it's an opportunity to conduct unique experiments and understand a little bit more about perhaps fuels and perhaps applications and perhaps other things that can help us go to other planets. One of the things about the microgravity environment, there's an absolute buoyancy and sedimentation. On Earth, heavy things fall to the ground and light things float, let's say in the water. That's not the case in the microgravity environment. There's this absolute buoyancy because of that. Also, there's the convection. Here on Earth, heat rises up. If you ever seen mom or dad cooking on the stove and you see the hot water boiling going upward, that's a gradient, gravity gradient that's causing that convection of heat away from the water. It's not the case in a microgravity environment, so we can take advantage of that too as well. Also, there's an absence of hydrostatic pressure here on the ground. As you go further down under the sea, perhaps, is that the pressures get higher and higher. In the microgravity environment, that's not the case. The pressure is the same. So we can take advantage of that and perhaps develop better material or metals in a liquid state that we can't do here on the ground. And then there's also this what we call the continuous float, which basically water is not contained in a container. It becomes a floating device. If you look here to the right, Scott, there's a little ball here. It actually looks like a ball, but it's really a liquid with some coloring on it. And so it's floating around in this microgravity environment. Interesting enough, water tends to become a circular object in a microgravity environment. Of course, you can do that experiment yourself. Just throw some water up in the air as much as you can, and you see it up into little bubbles, little balls, if you will, coming down to Earth. And so it's part of the advantage of doing experiments in microgravity environment in space station. There's also some of the other aspects, like conduct technology experiments. Right there, what you're seeing is what they call robotics fueling mission 3. It's hardware that was stored in the Japanese module. I think it's called Kibo. And this robotics fueling mission demonstrated the first transfer of storage of liquid methane, quantogenic fuel, fluids in the microgravity environment. This is important because storing fuel for the use of deep space is going to be very important. And we want to make sure that we develop perhaps containers or methods that doesn't boil away because of the cold temperatures of this stuff that has to be kept at very cold temperatures to in the liquid state. So these are experiments that we're doing with technology that potentially could help us in the future. And of course, we have to develop a better toilet. And, it may sound funny, but an toilet is something obviously that astronauts would like to have that doesn't require maintenance. What you're seeing here is a picture of an astronaut servicing the station toilet. Toilets, spacecraft have not performed well. Shuttle has a few issues, and space and also, and they're going to put a new toilet in that's going to be much better. So things like the development of better toilets is obviously very important for deep space missions. It goes back to having accommodations for the human that they can feel better, if you will, when they have some of the, for the better term, the luxuries that we're accustomed to here on the ground. And of course, the biggie is conducting human behavior and health experiments. That's a huge one because humans were not designed or were born to live in a gravity environment. So we need to understand what's it take for humans to live in another world for periods of long durations, especially Mars. It's a 3-year trip total for a max even for a short trip. And so here, Scott Kelly did like 340 days on space station. And he suffered quite a bit of setbacks as far as his health was concerned. He had they noticed that some of his DNA got mutated. They noticed also that his cognitive skills had declined too as well. He had other issues with his eyes too as well, blood pressure and things of that sort. So we have to learn how to protect the astronauts for long duration missions. So now let's talk about the Artemis program. It's going to be part of the proving ground on the moon. And interesting enough, Artemis was the twin sister of Apollo. So you got the Apollo program back in the 60s, and now we got the Artemis program, which they're calling now the Artemis generation. The young generation of people, they're going to be part of this Artemis program. And the objective here is to have somebody on the lunar surface, a woman, and actually the first woman and man on the moon by 2024. And so it's kind of a phased approach. So you first have the first human spacecraft to the moon in the 21st century, and then go to the first humans to orbit the moon also. And then we're going to be looking at things like, from a technology standpoint, high-powered solar electric propulsion. That's important for going into deep space. We need to get to Mars faster. And the faster you get there, the less exposure to radiation effects on the human body. And then we're going to have first pressurized module delivered to Gateway. We're going to have Gateway orbiting around the moon. And Gateway is kind of like the equivalent of the space station that we have right now. And Gateway is going to be the staging ground, if you will, for later humans landing systems delivered to the Gateway and to the ground. And you have a crew mission to Gateway and to the lunar surface. In the meantime, we also have commercial lunar payload services that are delivering payloads to the surface of the moon, like, for example, large-scale cargo landers to increase the capability of science and technology payloads, and then lunar landing systems, that land humans on the moon. And of course, you got rover as well, looking around for areas to explore, especially South Pole, where they plan to land the return to the moon. And then, of course, human boots on ground, as we call it. Humans are now going to live and work and operate in the moon environment. Of course, the moon has a once gravity So it does have a little bit of gravity, but there's no oxygen. The soil there is very abrasive. It can do a lot of damage to mechanical systems. So that's some of the things that we have to be cautious about when we're buying systems that can last for a long period of time without having to do a lot of repair uh, while it's operating in a viable manner on the moon. So let's talk briefly about deep space missions. Um, Space station, that's currently the one that's orbiting the Earth right now. It took about 40 missions to assemble such a large, massive spacecraft. The space station has almost 350,000 sensors with over 100 computer systems. And what the 3 astronauts or 6 astronauts or 5 astronauts we have right now cannot do that all by themselves. They're very dependent on Mission Control Center in Houston, Texas. And this is where you have the flight controllers. If you ever seen video or on television of mission control, it shows pictures of flight controllers. But it's just not the flight controllers that are looking at the space station. You got folks in the back. These are the engineers. These are the engineers that understand the systems very well in what we call the mission evaluation room, or called MER. And so you those folks supporting the flight controllers in Mission Control Center. And then you also have Moscow as well that are supporting space station. So you've got a lot of eyes and ears, if you will, looking at the space station, helping out the astronauts. Now, for the future, when we go to the moon with Gateway as part of the Artemis program, and even further down, we develop a Mars transport vehicle orbiting the moon, eventually go to Mars, is that the delays to the moon are not that bad. It's only about a 1.2 second delay. Going to Mars is a lot. So for the near term, we're going to have pretty much what we have going on right now with the Mission Control Center and support of the astronauts on the Gateway. And if you recall in the space program, Apollo program, Mission Control communicating with Apollo all the time, and even during critical events like landing on the moon on Apollo 11, where Neil Armstrong take over the autonomous landing system, and they land the Eagle on the moon, because the autonomous system was going to land them in a place where it was going to crash, basically. So Neil Armstrong had to take over, and obviously Mission Control was watching that and helping out, monitoring the systems. For going to Mars, because of the long delays, and especially for critical events, we're talking about something called onboard mission control, where the intelligence of the Mission Control Center people, mission evaluation room people, people from different countries as part of the onboard mission control center. So we're talking now the area of artificial intelligence, sometimes it's called expert systems, to help the astronauts. So you're just going to have maybe 4 astronauts, and they cannot handle all the data and all the maintenance and all the factors that are going to go into supporting these complex vehicles that are going into deep space. So they're going to have some kind of an assistant, the assistant in terms of a artificial intelligence system. And of course, there's some challenges there as well, because unlike here on the ground, where we have these huge rooms of computers, like, for example, Google, Amazon, the IBM Watson. These are large computer systems that basically provides artificial intelligence for search, for speech recognition, for things of that sort. But the computer chips are meant only for the ground and not for deep space. Radiation can basically kill the electronics. So that's going to be a major challenge too as well. I'll say more words about that later in my presentation. So we're going from what we're calling a crew mission control dependent operations to a crew vehicle dependency. The crew and the vehicle are going to have to depend on each other. So when they go deep into space, especially going to Mars, and that's why I mentioned the term Earth dependent when we go to Mars because of the distances. So there's going to be a lot writing on having the proper computer systems in place, the proper support infrastructure in place for the crew, so that way the crew and the vehicle can make the decisions autonomous by themselves and not having to deal with mission control because distances of the communication is just too long. So let's talk human spaceflight mission complexity and the challenges. And I'll just briefly go through these. Space shuttle was a complex system. I'm just trying to get a feel for complexity in space. And just to give you an example, here's an example of a product hierarchy. It's a 3 avionics system. If you look at it, it's basically 1, 2, 3 tiers. And so you had first the internal tank, the orbiter, solid rocket booster at the very high top level. But let's focus in on the orbiter. The orbiter was made up of the external structure, thermal protection system, avionics system, environmental control system, just a whole lot of systems, sometimes called subsystems. And then we go down to the avionics system and then kind of focus in and expand that, and you have the command data handling system, displays control system, instrumentation system, communication system. So you're seeing a breakdown of the different components from the level on that. And decomposition of this system is part of systems engineering, and that's you basically deal with complexity is to break down the problem into smaller, manageable problems that you can handle. So let's take the command data handling system. Part of that was general purpose computer. General purpose computers, there were 5 of them on the shuttle. 4 were basically the ones that were operating all the time, and then you had a 5th one, called the backup flight system, that would come up if there was a voting, misvoting, if you will, or disagreement on data. So purpose computers for the technology at the time it was a very complex, what we call fault-tolerant computing system. So let's take an interface that the general purpose computer spoke to, and that was the interface unit. So the interface unit talked to the main engine controller, and 3 of these, because obviously there were 3 engines on the shuttle. But if you look at the complexity of the main engine controller, and had a lot of interfaces to sensors and pneumatic valves, all kinds of things. So there's just a whole slew of information that's flowing to and from the main engine controller all the way back to the general computer, and then all that information was fed to the displays and systems, as well as sent to the mission control center for monitoring the space shuttle systems. Again, there was so much going on that mission control had to basically help the astronauts fly the complex vehicle. Right. So operations can be as complex as well. Orbiter processing facility. Here's the orbiter being processed, and we used to call the orbiter processing facility 1, and there were 2 of them, OPF1 and OPF2. Just a whole slew of people supporting the space shuttle maintenance and operations sustainment. It was incredible. At first, they sold the space shuttle as only needing 25 people in a hangar, kind of like a jet aircraft. In reality, because of the complexity of the system, it was more like 20,000 people in all operating and trying to maintain the space shuttle. And of course, operations, the launch tower and all the crawler, all these things that are part of the launch system are complex 2 systems as well. That was part of the system development effort. Mission control. Mission control just has a whole slew of computers and display systems that have to communicate with launch systems and as well as the communications once the astronauts are in orbit, and the space station, and in the case of Artemis, the Orion spacecraft, and all. So very complicated operations, and I just wanted to get you for the complexity of a human spaceflight mission. I'm using the space shuttle as an example. Now, there's challenges ahead, all right, especially going to space. And let's talk about the human needs and challenges and going into beyond Earth orbit, the moon, Mars, and beyond. As obviously we got to have water, all right. So water is a necessity for going to deep space, going on the moon. We got to have air. But water and air that exists readily on the moon. So we're going to have to generate our own. We just can't take a whole bunch of water for a whole year to accommodate an astronaut because of the weight of water. Each gallon of water, if we're talking U.S. units, 1 gallon of water is 8 pounds, and so you're talking about thousands of gallons of water to support the astronaut. It's just not feasible. So we're going to have to learn to generate our own water on another planet, generate our own air on another planet, food, generate our own food on another planet as well. We just, again, can take everything with us, especially if we're going to go to Mars. We got to have, to maintain our circadian rhythms for sleep. In some cases, for the most part, going to the moon, it won't be as bad as going to Mars, where the sun intensity decreases over r squared, where r is the distance from the sun to Mars. The health of the astronaut, physical health of the astronaut, the difference in gravity affects the body. As I mentioned earlier, or I may have mentioned earlier, that the microgravity environment, you're not producing as much calcium as you are here on the ground, because here in the ground, feeling that 14.7 pounds per square inch if you're on sea surface level, and so your body tries to counteract all that pressure. Actually, the 14 pounds per square inch is associated with the air density, and so it's trying to produce calcium to make strong bones. The effects of the one gravity environment, and then crew interaction. Okay, the team. So I mentioned about Star Trek and the diversity of the team. It's going to be important for the human, obviously, to interact in a team. Humans are social animals. We tend to be very social, and so we always want to be in the team and have that positive interaction with the team. And of course, under stressful situations, you want your team members to watch their back, if you will. And so that team interaction is going to be important. And of course, we may have a diverse crew, just like on Star Trek. And so you have different cultures, different belief systems, that play into the interaction between the astronauts. And of course, one of the biggest is the isolation, being away far from home. How's it going to affect the human? There's been various studies done on isolation, but it's still not clear what's going to happen to the astronaut when they land on Mars and they see Earth far away. I remember talking to a Russian scientist many years ago, and he was talking about some of the studies he was involved with, long duration studies in Siberia, isolation studies and stuff like that. It was interesting that he shared with me that in one experiment that a lot of the test subjects in the interview were talking about, we food, we managed to survive as a team and all this kind of stuff. But one particular test subject told this principal investigator, Russian scientist, he said, the real reason, he said, and this is coming from him, he said, the real reason I was able to last this long was because I knew I was on Earth, And I knew one day that door was going to open. And so that was the motivation for him to last that long. So we're not sure about the case going to Mars. That's something that's it's an ongoing investigation how to deal with that. Habitat. You don't think much of a habitat, but habitat's important. And as part of human systems integration, I'll mention a few words about that later, is that humans want a place that's comfortable to them, where they can retreat when they want to be alone for a little bit, get away from, the team members and whatever, and just be in isolation and maybe go read or do whatever. So a habitat design is very critical for a deep space mission, and even for way. So there's a lot of effort going into designing habitats for deep space missions. And the radiation environment. This is something that obviously is a biggie for astronauts. And it's not for the human electronics, and I'll say a few more words about that later. But radiation effects on human is certainly of a concern. It's a risk that the human research program is looking at as trying to how do we mitigate that. So and then there's something that's kind of associated with the psychology of the person is that any of these things or a combination of these things affect the psychology of the person. If there's not enough food, if there's not enough water, maybe the unit that's creating the water, what we call the in-situ resource utilization system, is not working properly. That's to worry the astronaut, or could worry the astronaut, and that starts affecting you. Think about yourself. If you're in a situation that's in a harsh environment and there's a lot of risk and hazards, how do you feel? You don't feel comfortable. And so you may make the decision in pressing the wrong button or doing the wrong task or the wrong activity and things of that sort. So that's another concern that we have as part of the human element. Human element, very complex system compared to hardware and software. So let's talk about technology needs, challenges. They got to have electricity. Right now, there's some research going on about nuclear power. These units are rather big, and they don't produce a whole lot of electricity at this time. And so, it's a challenge. And of course, you say, well, let's use solar arrays. You can use solar arrays on the moon to some extent if you put them where the sun is perhaps shining more often. But if you start going to Mars, again, going back to 1R square, the intensity of the sunlight requires that those solar panels get bigger and bigger. So how are we going to package bigger and bigger solar panels and put them on the moon, or on Mars rather? Things like nuclear power is probably the preferential way of generating electricity, but it has its own challenges as well. Lunar rovers, the human robot collaborative efforts is going to be important too. Rovers are going to be needed for going out and being the scouts, if you will, for the astronauts, and looking around and exploring the planet, the moon, or Mars. The habitats, as I mentioned as well, the technology associated with that, they got to work. They got to work 100%. You don't want them to be failing on you. Again, back to the risk and how it affects the human mind psychologically is important to environmental life support systems, an experimental unit that's being developed by NASA. And so environmental life support systems become very critical, because that's sort of provide breathing air for the astronauts. Imagine if that thing starts breaking down on you and you have so much air, what that does to you psychologically. Communications, even though we're going to be far away at Mars, not so much for the moon, but at Mars, being away and talking to loved ones is going to be a major challenge, for a 20 to 30 minute time delay in communications. So they're looking at things like laser communications as one possibility to speed up that communications. But that's only to Mars. What do you do when you start going further and further away? It starts becoming more challenging. And maybe that's something that we can come up with as using Star Trek, to call it Trekion mission communications, or I think the other terminology is quantum mechanics for communications, instantaneous communications. Of course, that stuff is all very early in the development right now, but some of the stuff that we're going to need in order to go to Mars and beyond. More importantly, computer systems. Obviously, they're going to be the brains of running all this stuff. The brains for the power systems, the brains for the rovers, the brain habitat system, controlling the environmental life support system, communications. Computers be very. They're going to be a very important part of that. In situ resource utilization, it too requires computer systems. This is a kind of a conceptual model of a situ resource utilization, which basically takes soil from the ground and extract from it water for drinking and for other purposes, as well as creating fuel for rockets, perhaps returning back to the moon. Again, all have to be very reliable. Landing systems on the moon. So this is very interesting. The Mars Science Laboratory, Curiosity, the weight of it was about 2,000 pounds. And talking to some JPL folks that I know were telling me that would be the maximum weight of landing a spaceship or a device, if you will, on Mars, because of the small amount of air and the speed that these spacecrafts are coming in from the Earth. That 2,000 pounds was the limit of how they landed it. If you recall, I think they call it the 7 minute of danger, or something like that. It had to come in at a certain angle into the Mars surface, and they had to deploy chutes, and then this rocket assistant crane basically would lower Mars Science Laboratory to the surface and then fly away. Well, all that works well up to 2,000 pounds. We're talking about huge systems like the habitat systems rather, that are going to be much more heavier. So how do we land something like that coming in at the speeds that they're coming in from the Earth? And of course, we're talking about kinetic energy, 1/2 mass times the velocity squared. And so how do you put out that amount of energy and safely on Mars? That's another challenge associated with deep space exploration. And of course, again, our old friend, the radiation environment, because radiation affects electronics, and we have to design electronics for dealing with the deep space radiation environment. Hey, so there's hazards and risk. And, we have an expected development and how we're going to develop the system and how it's going to behave. But hazards and risks lurking in a program. You got safety risks, injuries, loss of these assets, loss of human life. You got technical risks, autonomous dot control, payload power, things of that sort that are associated with technical risks or performance. Maybe degradation of performance is also a risk too as well. Cost risk, meet customer requirements as within cost. Going to moon Mars is going to be expensive. So we have to be cautious about dealing with the kind of risk that costs us a lot of money trying to develop systems that are suitable for deep space applications. And of course, you've got schedule too as well that affect the program. If you start flipping a lot, Congress could pull the plug on everything. So that's also as well. And but as Captain Kirk in Star Trek said, risk business, and that's what NASA does is to handle these kind of risks. And let me just talk about risks. This is adopted from James Reason, 1990 error. And so basically what I want to show here is that a hazard can occur or may not occur, but it depends on the barriers. And the barriers are what I'm representing here, the things that try to mitigate these hazards. You got the cultural organization, like, for example, the safety review boards, the critical design review boards, and things of that sort. Try to capture error, risk, or design errors and stuff of that sort. And in this barrier requirements, you're developing requirements. You're trying to mitigate a requirement. Design, you're trying to mitigate. You're trying to design and perhaps may not. You're trying to actually avoid flaws in the design. Safety, you're doing safety reviews, making sure that pressing this button is not going to cause an inadvertent activation of something that shouldn't have happened. Training, making sure that the proper training of the astronauts occurs and that they train as they're going to fly. Maintenance as well, making sure that things that the prints have the right torquing environment for torquing a bolt, for making sure that you inspect a cable before you stow it away, things of that sort. Health, making sure that the crew is healthy, psychologically, physiologically. If things, and what I'm showing here is somewhat of a altered form of the Swiss cheese balls or circular Swiss cheeses. But what I wanted to show here is that each one of these holes represents a hole in the barrier is a deficiency, and so there's deficiencies on each one of these barriers. And humans are they're not perfect. We humans can make errors. We can make errors in any of these barriers. And so these holes represent deficiencies, and these deficiencies, if you will, kind of notionally rotating over time. But there's a point in where the each barrier will line up a deficiency in each one of these at a certain period of time, where a hazard basically breaks through each one of the holes of the barrier that was meant to stop a hazard or some kind of error creates an accident. So it's I find this very interesting, human error standpoint of how things can line up. Chernobyl accident, if I recall correctly, had something like 15 different things that lined up in order for that accident to occur. So it can, and that's part of engineering, is to try to mitigate all that. So let me just talk briefly about how we do that in a risk process. So this is what we call the NASA Systems Engineering Engine, and it's basically the way how we develop systems in a methodical way. On the left-hand side is the system design process. We define requirements. We make sure that we understand what the stakeholders, and then we develop architectures. We look at different options, design solutions, and then we basically pick one solution based on cost, schedule, and technical performance to develop. And then on the right-hand side is the implementation, the product realization process. Basically, you start putting together systems, components into subsystems, and you first test the components, then the components to subsystems, you test the subsystems, and then after you test the subsystems, you test the systems. So you're methodically, incrementally putting together a system. And even though this shows somewhat of a linear process, it's not. There's some iterations. So, again, going back, you got requirements here, test plans, management plans, scoping your project, technical solutions, doing, again, trade studies, human in the testing, early evaluation of the human interfaces, architectures, prototype, you're doing final design, final specifications. You're now designing, you're getting to detailed schematics, charts for software. You start putting components together, fabrication of those components, and incrementally assembling and testing the system. And then you do system tests until you transition into the next level. And all during this time, you're managing the risk through the life cycle, because you got risk early on and you got risk later in the program. And that's what this part is basically the cross-cutting technical management processes associated with requirement management, interface management. Interfaces can kill you. Or can kill a project or cause some major challenges. So you got interface management, you got technical risk, configuration management. Configuration management, if you're not careful, you could be putting wrong software code into the right box or the right box with the wrong software code, and the thing doesn't operate. So you got to be cautious about configuration management. Decision analysis, also a biggie. You're always making decisions all the long way of the life cycle, which is here in the top shows. Formulation stage. If everything goes okay, around preliminary design review, you get the approval to start implementing, and that's the implementation phase of the NASA life cycle of a project. And then the human systems integration. Systems integration, we've always done human systems integration for the most part at NASA. It's a big thing for the Department of Defense. Basically, human systems integration is to treat the human equally as the hardware and software. And me as an engineer, I grew up in a world, or rather, I was trained in electrical engineering that you build the best hardware and the best software, and in the environment it's going to operate and system performance. In reality, it's the hardware and the software in the human, because you can have the best hardware, you can have the best software, but if the human does not know how to operate, or rather makes a mistake, the system as a whole has failed. So human system integration becomes very important. What you're seeing here at the top are the domains that NASA has identified that encompass or involves the human element. Habitability in the environment obviously affects the human, ensuring that the and living working conditions support the human health and performance. And training of efficient and effective mission training systems. Safety, minimizing and mitigating risks of personnel for the design meets mission success criteria. Human factors engineering, that's a huge one in human systems integration. It's kind of like the hub of it, and I'll show that in a minute. It's basically factoring the capabilities and limitations of the human performance, safety, and the satisfaction. Operations research, design for flight and crew objectives, including autonomy and automation, and maintainability and supportability, designed for optimizing the support of maintenance and support in given constraints. That's one of the shortfalls in the shuttle program, was the maintenance and supportability. The shuttle was so complex that it required a lot of maintenance and complicated maintenance, and it was driving the cost of operation. As the Department of Defense learned that after you built the project, it's really the cost of operating the system over time that gets really, really expensive. Over here to the left is basically the interaction of these domains with human factors engineering, talking to training, operations, maintenance, safety, habitability, ensuring that everything here from a human perspective has been optimized. And human systems integration is part of systems engineering. And what I'm showing here in a notional fashion is the interaction of human systems integration with program support and systems engineering. One of the key aspects of human systems integration is what we call the human-centered design. And the human-centered design is an iterative process of incrementally developing and testing the human interfaces, or human in the loop type thing. That's usually done as part of the training. So designs are not perfect. They're not perfect. They're human created, and so you got a hardware system here, and so this is what they call the bathtub curve. Hardware systems like component failures and stuff like that have a this is their let's call it their lifeline, if you will. So early on, you can have infant mortality, and that's why you burn in electronics, and that's what they burn in electronics, and that's a hardware system that once you burned in the electronics, that the failure rate is pretty constant and it's predictable. There's a exponential formula that's used for this. And then the wear out phase is basically things are getting old, whether it's mechanical or electrical. And so you have a wear out phase of the electronics, and this is where we want to operate. This is where we design systems to make sure that they perform reliably this time period. Software is a different animal altogether because the failure rate is not associated with anything physical, hardware, software, rather hardware. It's more of the software. So what you see here is kind of like a sawtooth waveform. But basically, when you first design code, you can have a lot of errors, and you try to fix all those errors. And then once you fix them, they have to create a new software load. And so you're going to have some errors, but then you're going to reduce the errors, and then you're going to have a new update, and then you're going to have rather errors. You're going to have to reduce that, and then again and again until you updating the software, and you just have a constant failure rate. Materials and manufacturing processes are not perfect either. You can, again, create materials and processes, but there's no guarantee they're going to be 100% reliable. And so you test for that, or you do analysis and things of that sort that NASA does as part of their development processes. Safety procedures and the human are 100% guaranteed to produce an error. It just happens. It just happens. You got to have things like inspections. Sometimes we call it 100% mandatory inspection points that got to occur to make sure that this thing is being assembled correctly. And then not all development testing gathers the necessary information. Development versus verification validation testing. So development testing is early on. Your prototypes are still being developed. You still don't quite know the requirements are still changing. And so your testing is being done, but with a low fidelity system. As you get further in maturing the system, verification and validation, that's where run for the record type testing occurs, is that validation testing, you're now testing with a high fidelity basic flight system. So you're getting somewhat a bit different result. But early development testing is very critical and very crucial. You're trying to ring out whether this thing's going to work or not in the first place. And by human error reduction, it's through loop type testing. So you have human loop testing that deals with skill human error, mistake human errors. Okay, so you can have memory lapses during the formation of the plan and before execution, and you have a plan in place, but errors can occur. You forget something, all right? A slip in an action, an unintentional action. It just happens to humans. Knowledge-based mistakes happen because you're still learning about the system and you're kind of evolving. So you're going to make a lot of mistakes. Rule-based types of systems occur as well. That you have rule bases in place, but perhaps the rules may not be the correct ones. All right, so testing ensures a high confidence that flaws are captured. So, all right, so we got human error that we got to deal with. We got to deal with hazards, mitigate those hazards despite the barriers. And through that process, we try to do that with good, solid systems engineering, as well as human systems integration. So collectively, with all that we learn and build systems that are going to help us go through other worlds. The technology systems, the systems for the human to keep them physiologically and psychologically healthy. And that'll help us go to other planets like Mars. And then eventually onto other worlds. All right. So that concludes. I'm going to stop sharing and return control over to host.
Yes, yes. Thank you, sir. It was really a wonderful session. So I will start asking some questions. So the most commonly asked question is that what technology do you need to reach the exoplanet?
What technologies do you need to reach an exoplanet?
Yes, sir.
Okay, so even when they want to go even beyond the solar system. um, the technology is probably going to be propulsive, taking us to other places in the galaxy quicker, much quicker. The it's amazing how and every time I think about it, it just it's hard for my mind around how big space is. So think of the Voyager 1, Voyager 2 that was launched back in the early 70s, 70, I think it was 1976, 1977. And it took it over 40 years just to get out of our solar system, right? The New Horizons space probe that went to Pluto much faster than Voyager, but it still took quite a few years. I think, if I recall correctly, years to get to Pluto. And frankly, that's the outside of our solar system, or outside of our solar system. Actually, there's a cloud that's outside of our solar system. But going to an exoplanet, if exoplanet that's maybe I don't know, maybe five light years away, that is a very far distance. Now, keep in mind that one light year is traveling at 186,000 miles per second. So if you multiply 186,000 miles per second times an hour, times a day, times a year, we're talking a long time, to get to an exoplanet. Basically, what will happen, I mean, at this point in time with the technology that we have, is that, we develop a probe that can hopefully go as fast as it can. And maybe 100 years from now, or maybe or more, that information comes back that the probe finally reached the exoplanet. It's just mind-boggling how far things are. And of course, with the Hubble Space Telescope, it looks back in time, and it's just, we're talking billions of years. Exo are light years away. The distances are just huge. So the technology of faster transportation is going to be vital. I'm sure about humans going on a trip like that. Maybe it have to be something like a starship that generations are going to live on, and maybe the 12th generation gets to that exoplanet. That's a good question.
So next question is, what is Van Allen radiation belt and how we can getting through it?
I'm sorry, can you repeat that, please?
Yes, sir. So what is Van Allen radiation belt and how we can get through it?
Van Allen belt.
Yes.
So so the Van Allen belt is it's located in our vicinity, and we have to get there we have to pass through it to get to the moon. Now, Apollo do that. So the challenge was to minimize the duration of the astronaut's exposure to the radiation of the Van Allen belt. So what we did was, as part of the computations, celestial computations, for trajectory of the Apollo space capsule to come in or go through the Van Allen belt at the shortest point of its location. There's inner belt and outer belt, and so the inner belt was the one of concern, and so they came in at the short point of the Van Allen belt, so they had a minimal exposure to the astronaut crew. I think the total exposure was something like 53 minutes through the Van Allen belt. And so, I mean, to get to it is pretty. I mean, it's basically setting the course. Just going just to the moon, for example. You're going to have Van Allen belt, but what you're trying to do, especially for humans, you're trying to minimize the amount of time that they're exposed in that Van Allen belt. And the best way to do that is to compute the best opportunity to cut through the shortest, let's call it the shortcut through the Van Allen belt to minimize radiation exposure to the humans and to the space systems.
Okay, sir. Okay. So there were one more question like, is there any substance which absorbs neutrons in the nuclear exploration?
Is there any substance that absorbs neutrons in space exploration?
Yes.
Well, yeah, I mean, there is. We've do something called radiation testing, and I mentioned about electron radiation effects on electronics. So we usually, what we do to see how well the electrons operate in the radiation environment is that we'll take them out to, let's say, take right now the place that we take high energy proton testing, a Boston hospital that basically is for radiation of cancer patients. We use that radiation beam to basically bombard the electronics with high energy protons, and then at Brookhaven, we test very expensively. We test for heavy ions. In both cases, what we do is that we areas that are vulnerable to radiation effects. Don't want them to be affected because we're trying to if this part's not work. We don't. The other parts may have to start the testing, but we're trying to protect it. So sometimes we'll put certain kinds of plastic in place, and sometimes we use copper or lead, and a lot of it, and it gets very, very heavy. So there's ways of mitigating ions and heavy ion. Neutrons, somewhat of a different beast. So, and I'm a radiation expert, but they are very high energy, and they basically go through a lot of things. In fact, the testing that's done at Brigham Young University, they use neutron testing to test a whole bunch of boards. If you think about saying, hey, we want to test 12 memory boards, they'll put 20 boards in parallel, operate them, and then they'll shoot a high energy beam through all 12 of them, and go right through all of them. So it's really hard to stop neutrons. Now, keep in mind, again, I'm not a radiation. If you're trying to slow down a radiation particle, sometimes you'll have something called spatulation, secondary effects. So what does that mean? Something like if you're trying to slow down, it could hit something that basically, if you know what billiards is or pool, that you have a cue ball that hits the billiard balls and they scatter. So what was you're trying to slow down one particle? All of a sudden, you've created many, many more particles that could create even more damage. So there's a trade on whether you let the particle go through or you stop.
So one more interesting question from participants. There are any space mission dedicated to the Ticons? Ticons means which is fast and light.
I'm sorry, could you repeat this?
Is there any space mission dedicated to search a Ticon?
Dedicated for what now?
Ticon means which can move faster than light. Very long back, yeah.
Oh, tech hounds. I'm not aware of one. I wouldn't be surprised if they do. Again, going back to communications is finding a way that perhaps in the quantum world we can communicate much faster. Right now, our conventional way of communication using radio frequencies it's just too slow. And if we're going to go out into space, deeper and deeper to space, we're going to have to find better ways of communicating, faster ways of communicating. And certainly on Star Trek, they use that kind of communication, so to do instantaneous communication. It's just not there yet. Quantum computers, the world of quantum mechanics, is kind of some people call spooky stuff. And that's some of the work that I think a lot of these students out there that are listening may be doing, and hopefully they'll be doing, to find better ways of communications, because that's going to be important. I mentioned previously the psychological effect of human, and I think everybody can relate to that, is trying to keep them healthy, and one way of keeping them healthy is to communicate with their loved ones, and especially if it's video and audio. Right now, I've listened to or I've read some of the astronauts, and they say that being on the space station, communicating with loved ones is basically a way to prep up. That they feel really good after they talk to their loved ones, and so it's definitely something that's very critical for deep space missions.
Okay. Okay, sir. So I will ask the last question, right? So, as it is possible to design fully self-sustainable spacecrafts as theoretically, so whether it might be helpful in the deep space mission, how will you explain about this concept or how it can be done?
You mean a rotating spacecraft? Did I hear that
Yeah,
correctly?
well, sustainable spacecraft.
Okay, so is this referring to creating an artificial gravity?
Okay, artificial gravity.
Okay, yeah, artificial gravity and rotating spacecraft. Yeah, so that concept has been around since the days of Werner von Braun, who was actually instrumental in developing the Saturn V rocket that took us to the moon. Rotating spacecraft, yeah, it's doable, but at least the computation, some of the readings that I have looked at, or reports that I've looked at, we're talking about a very, very large mechanical system that's going to be rotating. And so the question arises, well, how are we going to do that? Well, how are we going to build it? Maybe you can design it, and sometimes designs look real pretty and everything, and everything looks hunky-dory on a piece of paper, but implementing a manufacturing becomes more of a challenge. And so these rotating spacecrafts, the challenge is building something of that large complexity. And then secondly, and perhaps more importantly, is the reliability of something that's rotating. That how do you protect it against strike from a meteoroid that perhaps jam it? And so it's one of those areas of systems engineering where you develop you look at risk, and then you look at the risk of mitigating it. So it's doable. It's just it'd be obviously very expensive, very challenging. And then I've heard depending on the situation, some people will get nauseous just being rotated around. If you've ever been on a ride at the places, entertainment parks, if you're going around in circles, after a while you get a little, and you might get a little nauseous, especially after you eat something, and you don't feel well. So there's pros and cons for developing those systems. That's something that, again, maybe somebody out there in the audience, or there's some students that will start developing some concepts. for developing something like this in space that is very reliable and handles the deep environment, not so much just the cold and hot, but also the effects of high speed meteoroids that could hit like this and damage it and perhaps compromise the mission.
Okay. So similarly, one more thing they have, sir, is it possible to use a nuclear elements like uranium and thorium for sustainable energy sources? Is it possible apart from that?
Yeah, yes, it is possible. Now, plutonium and there's they're called RTGs. They use them on deep space probes, radio electric generators, and so they use plutonium. We're in short supply of plutonium, and it's going to be somewhat of a challenge to generate or create large RTGs for exploration on other planets. And so those obviously you can use uranium, but uranium 235, 236. Obviously, you got to be cautious about the radiation exposure to the astronauts and perhaps affecting electronics. So it is possible. There's just more cautious in place. And then, of course, you have to get all kinds of approval for using that for deep space mission. And obviously, becomes more concerning. You have humans because humans already have to deal with the radiation effects of galactic radiation. And if you have nuclear power sources that are riding on a spacecraft going with you to another planet, or maybe after they've landed, maybe they're not going together, but they land separately. But you still have something that potentially cause radiation exposure to the astronauts is something that world of human systems integration and systems engineering have to look at the possible the hazards, the risk associated with that hazard, and how are they going to mitigate that risk?
Okay. So, last question. This will be the last. Many people have asked so much of questions. I will compile and give you. The last question is how can Indian students qualify for NASA?
Okay. So how can they apply for NASA? All right. I get that a lot.
Yes.
So here's the thing. When you say NASA, okay, so NASA basically a U.S. government entity, and so to come work for NASA, you have to be a U.S. And even working with even if you're a contractor, support NASA, like let's say Lockheed or some of these other companies support NASA. Many times they have us as U.S. citizenships, but it sounds like a very challenging thing. I can share with you there is a Indian student that I met. Oh gosh, this was like 5 years ago. So she was at the time in her second year in college, and he wanted to come work for NASA. I said, you're going to have to somehow come to the United States and become a citizen, get a citizenship. And so, I don't care just how I can do this. And so I said, well, look, you're going to graduate from college in India. And then I went, come over to the United States and apply for your master's degree at university here. And then find a professor that works with NASA. So fast forward, and so she got accepted to Syracuse University in New York State, eastern part of the United States. And so she got her master's in computer science. And she transferred over, rather she applied for a PhD at San Diego State University, where one of the professors that teaches there works at Shepherd Laboratory, which is one of our NASA centers in California. And so she got accepted to that PhD program. And I had suggested to her to get into machine learning and artificial intelligence because that was biggie for NASA in the coming years. And that's where she is right now. And so she she basically tore down every barrier that was in front of her, and she's just not too far away from eventually working a project with her professor with NASA, and maybe one day she'll get her citizenship and work for NASA.
Okay, sir. Okay, that's wonderful, sir. That's wonderful. So, okay, sir, here we will end our session. I would like to give the vote of thanks. So, on behalf of our entire team of Wings of Arrow and the society and the supporters, first of all, I would like to thank the Almighty for making this event a successful one with His blessings and grace. So, then I would like to thank to our chief guest, Mr. George Salazar, who spared his time from his busiest schedule to grace the occasion. Today, we had an opportunity to hear from your thoughts about microgravity to many other challenging technology where it has encouraged us as well as to the participants. And I would also like to thank to the Wings of Arrow family who have worked behind the scenes for the like large amount of cooperations in making this event a successful one. So finally, I would like to thank our supporters, our participants who are always actively participating and looking, focusing more interest to participate. And thank you, one and all present here. So, Mr. Salazar, now we will thank you once again, sir. And now we are demonstrating about the how to download the certificate for the participants. So, if you have time, please stay back with us, sir. So now we will proceed with the downloading procedure, sir. Okay, sir. So, Professor Ponmakishan, so will you please explain how to download the program certificate for the participants? I request participants please follow the procedure step by step so it will be helpful for you to download. And one more thing I would like to say that this is a TEMS era platform where you're going to download the certificate, and it will not only helpful for you to download this course. We have ample of course, international courses, webinars. Please go through the courses and please attend the courses based on your domain, right? So it will be little like different from other platform where you can easily avail your certificate. Please follow the steps so it will be helpful for you to download this certificate. Please go through it. Please, Kishan sir, proceed with your session.
Yeah. Well, thank you for having me. Bye bye.
So, yes, sir. Bye. So, dear participants, I hope you might have got the link for today's webinar. So, if you have not yet got, kindly look into the screen temps.wingsofarrow.in. Okay. So, as we have got feedback from our previous webinars that for logging in or for signing up, it is difficult. So, we have collaborated and incubated with Google Sign In. So you can use your Google sign-in to enter into our platform. Okay. So or if you are using your own account, you can create your own account. Okay. So if you are having any issues with username as well as password, you can contact us anytime. We have given the contact details over there. So kindly use that. Okay. Right. So once you have successfully logged in with your Google account or with your username and password, the front page will be opening where you can find today's session, challenges of future space mission. Okay. So once you click the space mission, it will ask an access or enroll. So you can enroll in that particularly. So after enrolling, you will be getting into a main page. Okay. So we request you to use desktop mode if you are using in mobile. We request you to desktop mode since our platform is still under development for mobile versions. Okay. So the live video is displayed over here. So I request all the participants to give the questions in this space mission forum. So whenever we are having a free time, we will give to George Salazar sir. So when he is having free time, he will respond to you there itself. And once you given your question in the mission forum, your lecture feedback will be opening. Okay. So make sure you are giving your questions and queries in the space mission forum. Automatically the lecture feedback will be unlocking. So once you have given the lecture feedback, so your lecture certificate will be unlocked. Okay. So you can download your lecture certificate from this platform. So there is a question from participants that why we are complicating that certificate pattern, or many institutions from India, they are using Google form, right? Feedback form. So we don't want to be like the feedback form givers, and those who are not even attended the session, they will be getting the certificate. So we don't want to dump the participants to for certificate. So they want to learn something. That's our motto. And we have done this lectures, so many lectures previously also. We have done this lecture also, and also upcoming lectures, international lectures, for free of cost. Our participants can learn. Our motto is to make a bridge between the scientists of international organization and the students community. So with this, I'm ending my session. So if you have any queries in downloading the certificate, you can always mail to us at admin@tems.wingsofaero.in, and you can call to this number also. So we will be ready to answer you. So with this, I am ending the session. Thank you.